recording again? Great. All right, welcome back everyone, and thanks for taking the pretest. It's my pleasure to introduce today Michael Strauss, who's a professor at the Department of Astrophysical Sciences at Princeton. Michael studies galaxies and the large-scale structure of the universe, and our investigation today is about the large-scale structure. So this is a really nice fit to have Michael as the expert to speak with us today. He and his colleagues have discovered some of the most distant quasars ever found, going back to a time when the universe was less than 1 billion years old. And so I give you Michael. Thank you.
Well, thank you, everybody. I imagine you can hear me and see my first slide. I have 15 minutes where I have to describe the entire structure of the universe. We'll see how far we can get here. And in particular, I want to emphasize, and the theme here is how observations of how galaxies are clustered with each other give us understanding and hints of our current cosmological model. So let's look at an astronomical image like the one on the previous screen or this one here. And what we see when we take a picture of the sky is everything in 2 dimensions. It looks like as it were, a flat piece of paper, or if you look at the whole sky, a dome, sometimes called the celestial sphere. We really only see 3 dimensions. We do not have any depth perception when we look at an image like this. And in fact, in an image like this, there are both stars. If you can see my cursor, I'm pointing at a few stars in this field, which may be at distances of a few thousand light years, practically next door, if you're an astronomer, to distant galaxies, which may be tens or hundreds of millions of light years, some of these fuzzy dots that we see here. What's shown here is a representation over a very large chunk of sky. This past one was a zoom in of a small piece of sky. Looking at a large piece of sky, there's each dot in this image, and there's about 400,000 of them, represents a single galaxy. And again, we're emphasizing the statement that what we see here is all projected into 2 dimensions. And what we really want to do, if we want to understand the large-scale structure of the universe, is to get that 3rd dimension. And redshifts, which is a concept that I understand you have been exploring in this whole seminar, is the mechanism that we use to map objects in 3 dimensions. I noticed someone asked a question earlier, where do all these data come from? The pictures here, the last 3 pictures indeed, have all come from data from what's called the Sloan Digital Sky Survey. And we'll tie that into the Rubin Observatory right at the end. So what a redshift allows one to do is to determine from the spectrum of a galaxy how fast that galaxy appears to be moving away from us through an effect called the Doppler shift. And the relationship, and it was Edwin Hubble back in 1929 who published the results showing that the redshift, or the speed or velocity that a galaxy seems to be moving away from us, is proportional to the distance that galaxy is from us. And so that's stated in the lower left. The recession velocity, which is something you can measure directly by measuring the spectrum, is proportional to that distance. And indeed, we now refer to that relationship as the Hubble law in Hubble's honor.
Thank you for calling the Kroger Pharmacy. If this is a medical emergency,
someone
please
may
call
want to hit
911.
Someone may
Save
want
up
to hit a
to
mute on
85%
that
on
one.
With the Kroger RX Savings Club. Now accepted here. Many prescriptions are just $6.
Okay, can people still hear me?
Free. Visit KrogerSC.com, download the Kroger RX SC app, or ask us for details.
Oh, and in Spanish too. Okay, so in the upper left, we actually see one of Hubble's original diagrams.
Phone, please enter your 7-digit prescription refill number.
I think it's Lisa Brown who perhaps needs to mute there. Okay, so on the upper left, we see Hubble's original diagram. The data that he had back in 1929 was, oh my goodness. Again, Lisa Brown, if you could mute.
If this is correct,
I think
press
that would be
1
good.
to re-enter your
Okay.
Please
So,
enter the last 4 digits of your telephone number.
Okay, so on the y The y-axis again is the velocity or the redshift that Hubble measures. The x-axis the distance, and he had pretty crappy data back in 1929. You can look at those points and say, well, I think there's a relationship between these two, with much better data, and as shown in the lower right, this is data from in the last decade or two, one compilation of very accurate measurements of redshifts and distances, and you can see that there's a beautiful relationship between the two, and that is our direct evidence that all galaxies are redshift and the universe is expanding, which is indeed one of the questions that people had asked. So with those redshifts, if you measure the redshifts of the galaxies, one at a time or many at a time, then you can actually put a galaxy into 3 dimensions, and you can see how far or how distant any given galaxy is. And so what is depicted here is about 10,000 galaxies, each dot representing one galaxy, now put into 3 dimensions. Now we're taking a 2-dimensional slice, not a projection, but a slice out of that 3-dimensional distribution. And you can see that the distribution is incredibly rich. The galaxies are not just randomly sprinkled out there, but form into a variety of large structures. And indeed, people have noticed this, what's called the Sloan Great Wall, this enormous distribution of galaxies stretching across what are hundreds of millions of light years in this particular case. So, and if we step back further, and again, this is still all data from the Sloan Digital Sky Survey, we can get some sense of the full richness of the galaxy distribution. The survey did not cover the entire sky, which is why there's these empty regions, these empty wedges here, but this is, again, a 2-dimensional slice through the 3-dimensional galaxy distribution, and you can see it is indeed very rich. So this is a movie, sort of another representation of the data that we've been looking at, now showing the full 3-dimensional structure here. An actual galaxy image has been put in for each galaxy. The galaxies have been put in the right place, and this movie sort of flies us through this incredibly beautiful and rich structure that one sees. And you can see that there are regions where galaxies are very clumped together. We call those clusters of galaxies. Other regions that are almost completely empty, we call those voids, and so on. And we could spend quite a lot of time looking at this movie, but I have limited time, so let me just go on. But you can see, you can get some sense of the richness of the galaxy distribution. So, you know, as astronomers, as scientists, we want to ask, well, what's going on? Where did all this rich structure come from? And to do that, we really want to look at a different kind of map. And as I think you know, the universe is expanding, which meant that in the past it was much denser than it was today. It was much hotter than it was today. And one of the things that hot things do is that they glow. They give off energy, what's called thermal radiation or thermal energy or black body radiation. Those are all sort of equivalent terms. So anything that's sufficiently hot will glow. And it was realized first in the 1940s, but then discovered in the 1960s that if the universe was once very hot, then that the radiation, the light that the universe gave off because it was hot, will not have disappeared. It should still be there. Hot things give off light, and so we can hope to see that. This prediction was actually confirmed in a serendipitous discovery by these two gentlemen, Arno Penzias and Robert Wilson, in 1965, saying, we used this telescope, you can see radio telescope in the back, and we saw evidence of light coming from all directions that indeed people very quickly realized was indeed the leftover heat from the early stage of the universe. So in pictures that I'm about to show, what the statement is that this comes from all directions. So we want to look at the full sphere of the sky. We've talked about the celestial sphere, and so we have to make pictures that involve the whole sphere. So we're going to take a globe, as it were, which is a spherical shape, and turn it into this egg shape ellipse that you're seeing. So pictures that you're about to show represent the full sphere of the sky in this elliptical shape. So that just sets the context there. So here's a picture of what was measured from the cosmic microwave background. The statement, as we've just heard, is that, as Artis was just saying correctly, the Big Bang happened everywhere at once. There is no center to to the universe. And so the cosmic microwave background, CMB, is coming to us from all directions. And therefore, one would expect that the intensity of that light that's coming to us from all directions should look exactly the same. And here is, you know, in some sense, the most boring map in the world. It's the accurate measurement of the intensity of that light, here expressed in temperature units. It would take a little digression to explain that. Basically, the leftover temperature of the universe as measured over the entire sky. Beautifully uniform, just as we would have predicted. So then you say, well, okay, well, that's kind of cool. But the universe, so the statement is that, as already been hinted, the light from the early universe, we're seeing it, as it turns out, at a time when the universe was about 400,000 years old. Looking at this, you say, well, the universe 400,000 years after the Big Bang was incredibly smooth. And yet we live in a very structured universe today, as those pictures we were just looking at. So maybe it's not absolutely perfectly smooth. There may have been regions that were slightly denser with a stronger gravitational pull. They pull material into them, making things denser still, increasing the gravity and pulling in yet material. This is called the process of gravitational instability. That's the fancy word. Jim Peebles, one of the world experts on this, likes to phrase it in a much more pithy way and say, gravity sucks, which is really a statement about how gravity pulls things together. So indeed, hidden in that smoothness of the CMB must be some very, very low level, subtle fluctuations or undulations from which the current structure of the universe arose. So basically, we want to go back to this picture and crank up the contrast and see what's going on. And so here, the upper panel is the original picture, and these data come from a satellite called the Cosmic Background Explorer, or COBE, and these maps came out in the early 1990s. The upper plot, again, is the one you had seen before. We crank up the contrast a lot. There's an overall pattern, which I don't have time to describe, which turns out to be due to the motion of the Earth relative to the universe as a whole. There's a lot to unpack in that statement. But if you correct for that or take out that piece, what you see remaining, there's the band across the middle, the bright band is actually the Earth, is the Milky Way in which we're embedded. That's a detail, but the blue and green and red above and below the bright red bar are the intrinsic fluctuations in the cosmic microwave background that are at the level of 1 part in 100,000. And these in a soundbite are basically the fluctuations out of which the large scale structure of the universe grew. So this was 1992, state of the art. We've made a little bit of progress since then. This is now about 10 years old, the Wilkinson microwave anisotropy probe. There's actually a more recent satellite that did it even better. But here is a representation now corrected for the effect of the Milky Way, which is why you don't see that bright band across the middle. And now a highly accurate map of the fluctuations in the cosmic microwave background. So it is not perfectly smooth. It's awfully smooth. 1 part in 100,000 are sort of the level of the fluctuations. But cosmologists are very interested in trying to understand how the relationship between this and the modern day structure that we see in the distribution of galaxies. So indeed, let's explore that. I had already described Jim Peebles' gravity sucks idea that says that dense regions will become ever more dense as the gravity, as they pull in material around them. And here's just a very series of slides from a computer simulation that shows the distribution of matter clustering under the effects of gravity. In these series of snapshots we're about to look at, we've taken out the effect of the expanding universe. So the boxes are not getting bigger and bigger. They basically have corrected for that detail. But as we go forward, we see that things get ever more clumped as time goes on. And you can see that when you model this process on a computer, you start getting a distribution of, in this case, dark matter that is reminiscent of that structure that we had seen in the galaxy distribution. So indeed, people do more than look at pretty pictures, pretty though they are, and try to come up with statistical measurements of the structure in the cosmic microwave background maps and measure quantities called correlation functions and power spectra, and there's a variety of technical terms that we can describe that that quantify in some detail what the nature of the clustering of both the galaxies that we can see in the present day universe and the fluctuations in the early universe are, and try to relate the two. And that whole program has been enormously successful. So here is a plot from a paper that was released literally last week. This is the current state of the art of measurements of the cosmic microwave background. Without going into technical details, the x-axis in this plot measures the range of scales over which we're measuring clustering. You look at the upper axis, you see 90 degrees on the left-hand side, 0.05 degrees. We're going from large scales to small. That's the quantity on the x-axis. The quantity on the y-axis is measuring, actually, as it turns out, a variety of different quantities that are related to how strong the clustering is on that scale. The various dots are measurements from a variety of different experiments. The brand new one that was published literally last week is the so-called Atacama Cosmology Telescope, ACT, which was, those are the red points that you see, and this paper was showing these latest results. And the line that goes through the points is the theoretical prediction of our modern cosmological model. And you can see that the data in the model are an exquisite and beautiful agreement. And of course, a full explanation of what's going on in this graph would take an hour or more to say all the wonderful things that are going on here. Here, this is perhaps a little less dramatic, but this paper was released just a few days ago, making the latest measurements of the clustering of galaxies. And it's one particular representation of the power spectrum, measurement of clustering. Now the x-axis, again, is scale, but large scales are on the right side instead of the left. It's just, and in this particular paper was emphasizing these sort of wiggly characterizations. And although this is perhaps a little less dramatic than the previous one, again, there's beautiful agreement that our modern cosmological model and the observed clustering of galaxies are the same. And even though I haven't explained the detail, the wiggles that are seen in here and the wiggles that are seen in this plot from the cosmic microwave background are basically the same kind of wiggles. It's the same physical effect that's going on. Okay, so the statement was, we have a cosmological model and works beautifully, everything's understood, right? Well, it turns out that this model, on one side, is very simple. The total number of free parameters or things you get to fiddle with to match all these beautiful data is about 7 numbers that you have to fit. It's an astonishingly simple model in that sense. We're fitting all those distribution of galaxy data and all the cosmic microwave data with roughly seven numbers, but it requires some very strange ingredients. It requires dark matter, saying most of the clustering in the universe is dominated by matter that we don't see, and dark energy, which is even more mysterious, which is causing the expansion of the universe to accelerate. Without those ingredients, our program of trying to fit the observational data would fail miserably. And that was realized starting in the 1970s. But so dark matter and dark energy are colorful terms. But if you ask me, okay, so what is dark matter? What is dark energy? Those are the Nobel Prize winning questions that I would love to be able to answer. We really do not know what either of those are physically. Of course, we know a lot about what they aren't, and we can say we know some things, but and we know how much there are. Again, I gave you the numbers right there. And only about 4% of the total mass energy density of the universe is composed of ordinary stuff like galaxies, like atoms, excuse me, that make up stars and make up planets and make up living creatures like ourselves. So how much time do I have? I'm almost done. But if I can go for just a little bit longer. Let me just say that when we one of the big questions is to explore how the large-scale structure of the universe has changed with time, and how whether dark matter and dark energy themselves have changed interestingly with time. And with a powerful telescope like the Rubin Observatory, we can hope to, looking at faint and distant galaxies, we can hope to see the universe as it was in the distant past. So here's an artist's conception of the Rubin Observatory, and I guess I'm out of slides. I thought I had thrown a few more in, but one of the key goals for the Rubin Observatory is to map out the distribution of galaxies at very large redshifts, therefore earlier in the history of the universe, and explore the large-scale distribution of galaxies and dark matter, and to try to understand and hopefully get a crucial clue as to what the nature of dark energy and dark matter are, or whether our cosmological model has some ingredients that we haven't yet invented yet. So let me finish there. Thank you.
Thank you, Dr. Strauss. We do have a few questions from the chat box, and the first question is from Jarvis. He says, why are there periodic oscillations in the scale of the clustering you showed on the previous slide?
Yes, so those oscillations that you see here, and indeed it's basically the same physics that gives the oscillations here. The technical term are baryon acoustic oscillations. Those ultimately arise from sound waves that took place in the universe before. So I mentioned that the cosmic microwave background that we're observing, we're seeing it at a time when the universe was about 400,000 years old. That comes from the time when the universe cooled enough for neutral atoms, ordinary hydrogen, to form. Before that, it was too hot, and the atoms were torn apart into the constituent protons and electrons. At that time, when the universe, before 400,000 years, and indeed somewhat before that, sound waves could actually propagate through the coupled photons, the light, and the ordinary matter in the universe. And those sound waves are basically imprint themselves onto the cosmic microwave background, and indeed on the galaxy distribution as well. And by measuring that in detail, we can understand the physics of those sound waves, and actually gives us key clues as to how much dark matter and dark energy there is.
Perfect, thank you. We have time for two more, and then one is from Rosemary, and although I believe artists might be able to assist with this one as well. I vaguely remember some online tool that lets you vary the percentage of dark matter, dark energy, and see how the oscillations change and the power spectrum changes. Is there an educational tool like this?
I have seen such things, but I can't quote them off the top of my head. Maybe artist knows more.
Yeah, and artists, feel free to jump in the chat box if you can think of one. And then finally, Dr. Strauss, one last question from Martin. It says, to find a distant quasar 1 billion years after the Big Bang suggests supermassive black holes have already formed. What's the current thinking on there being enough time for them to form?
Oh, that's a good question. Okay, so I didn't have a chance to talk about this. So as I guess artists pointed out, one of the things I like to do is go find distant quasars. Quasars are, I'm just repeating the context of this question. Quasars are powered by supermassive black holes, hundreds of millions to billions of times the mass of the sun, and as the question implies, that it's only 1 billion years after the Big Bang, and you have to form such a massive black hole in that relatively short amount of time. Again, the early universe, let's go back to the early universe, 400,000 years after the Big Bang, the universe is almost perfectly smooth. The deviations from perfect smoothness are 1 part in 100,000. A black hole is the opposite of perfectly smooth. It's the densest thing you could possibly imagine. And so how did the universe go from this to forming those black holes? This is a big question. I don't have a full answer to that. Every time the astronomers find quasars, and therefore supermassive black holes, at ever higher redshift, therefore ever earlier in the history, they make this question ever more pointed. When we first started finding quasars that were only 1 billion years after the Big Bang, there was the people who do these models for a living thought that they could explain that as that redshift record has crept upwards. So now the current record is about 750 million years after the Big Bang, and the black holes that power them are about 1 billion solar masses. The question is getting ever more acute. So this is all to say, I'm not going to give you a single clean answer to this question, but it is a good one.
Thank you very much, Dr. Strauss, for all your time today. Artis, we'll give it back to you.
Thank you very much.
I should stop sharing, I guess.
Yeah, so I appreciate your time. We're getting a lot of nice comments in the chat about how this is a fascinating and great talk. So I believe, I don't know if we've talked about this, but have you made your slides available to me so that we could post them?
Yes, I sent you an email
Okay.
with them. And
Okay,
yes,
so-
I don't think there's anything top secret. I think everything is public, so,
Yes,
so
everyone likes
free to share them.
Great. Okay, thank you. And I will post those later today, just so everyone knows.
Okay,
All right.
very good.
Thank you
Okay, so
much.
is there a reason for me to stay around, or?
You do not need to.
Okay.
You're welcome if you want, but you're certainly welcome to leave as well.
Okay, I do have other things to do. So thank you all. Goodbye.
Thanks. Goodbye. Okay, we're going to take a break in a minute, but I think in the interest of time, since we allowed Dr. Strauss to go over a little bit, what I'd like to do right now is give you the instructions for what you'll be doing in the breakout room so that you can come back from break and immediately begin to work with your group. So as before, please remember to introduce yourselves to everyone, pick a facilitator to share their screen, and the app that we're going to be working on today under the resources is called Exploring the Observable Universe. If you have time today after the app, please begin taking the pre-test, post-test again. You'll see on the schedule that we've allocated 10 minutes before the homework wrap up at the end of the workshop. But I think what's easiest for us to do at this point is just allow you to work through seamlessly and not have to come back and take the post-test. So in your group, when you finish your app, if you would please take the post-test. If you have additional time, I encourage you to take a look at our teacher guide today, because we are going to be asking you a few questions about it on our homework form tonight. And you certainly can talk about the pre-test, post-test as well. We're going to call you back from the breakout room, as we've done before, about 5 minutes before the end of our session, just to go through the homework and address any final issues. So with that, let's take a break. And when you come back, you'll be invited to join a breakout room and you can begin. Thank you.
When are we coming back?